Thanks again, Pete. And thank you all for coming. I know it's a little bit early, and I appreciate you coming here to hear this talk. So I'm going to talk about a sort of a unique project. It's in a watershed within Redwood National Park called Lost Man Creek, which is a tributary to Prairie Creek, which is a tributary to Redwood Creek. It's down low in the watershed. Most of it is parkland at this point in time, and a lot of that is old-growth redwood, but not all of it. The park inherited a pretty, in some areas, dense network of old logging roads and skid trails, and beginning in 78 or 79, embarked on a program to treat a lot of those roads, money permitting each year, to reduce the erosion threats permanently. So, and before I get going, I want to make 2 points. Number one, let me see if I can work this mouse today. There it is. This is actually Little Lost Man Creek. It was one of the control streams in this study. And in a lot of storms, this is as turbid as it gets. It's pristine, but it's what I call a dirty, pristine watershed. So it's got higher natural erosion rates than some other areas in Prairie Creek. The other one is that not all studies work out. And there are a couple of aspects of this one that I'll talk about that were not successful. One is being very confident about teasing out the effects of the road decommissioning program. It's what I like to call collateral damage from watershed restoration. And, well, I think that's enough. We'll get going here. So, as I said, the park inherited, in some places, some pretty extreme ground disturbance areas with lots of roads, high density, and a lot of skid trails. And really, the park, there's so many more miles of skid trails out there that it's really hard for any entity to treat all those. So the focus has been on logging roads, haul roads. And I think probably all of us have seen photos of the problems with road stream crossings. They can, the culverts can plug, and the road bed itself can be gullied, and gullies can extend far downstream on the hill slope. Some in the lower left, you see, can cause debris torrents that scour channels and deposit large amounts of sediment in the downstream reaches. And that sediment degrades, and it destroys habitat for fish and causes lots of other problems. When you have an degraded channel, the floodwaters are that much higher. And so they're eating away at banks that were previously unaffected by flows and creating landslides. And like I said, one of the resources we care a lot about is fish, but there's a ton of other ones. Hart Welsh, who's here at the conference, has been studying salamanders for a long time, and the effects actually in Lost Man Creek of some of the road decommissioning work. So I think beginning with my master's thesis in the early 80s, people have been trying to understand some of the effects of this restoration work, mainly focusing on the amount of post-restoration erosion from stream crossings that were excavated. And my results from my master's thesis, I looked at 24 sites. They averaged about 27 cubic meters per site. Mayday looked at quite a few. I believe they were in Redwood National Park, averaging about twice that. Some other ones, and for example, the Upper Mattole I was involved with, much lower. And I think the later these crossings were excavated, the better a job was done in getting out all the fill and reducing post-restoration effects. One of the largest one was done by Pacific Watershed Associates down at the bottom here. 275 crossings, average about 26 cubic yards. That's about the same as my thesis. And these distributions of erosion volumes per site are very skewed. A few sites will erode tremendous amounts, most moderate to small amounts, and some hardly at all. And this is a photo from my master's thesis. Believe it or not, that's me 34 years ago. And this is a before and after winter shot of one of my study sites that had a lot of woody debris in it. And it was small woody debris, but even so, I think it really prevented a lot more erosion from happening than actually took place. Not so with this one. The soils were more erodible. There was less coarse fragment in the eroding materials, so it couldn't form a nice armored lag. And some of the volumes I measured were quite large, both pre and post treatment. And this is the Redwood Creek watershed, flows of the Pacific Ocean. Let me see. I'm not working this mouse very well. Near Oric, California, about 40 miles north of here. And the lower portion that looks more white is Redwood National State Parks. Most of it, that is. And you can see that when the park was enlarged in 1978, there was quite a high density of roads. And then as of 2000, you can actually, it's noticeable after the progress of the road treatment program, they're a lot less dense. And they're even less dense today. And I keep losing this. Lost Man Creek that I'm going to talk about is this part of the Prairie Creek watershed right here. And here it is, a little bit closer. The green areas are old-growth redwood. The sub-watersheds are delineated, and gauging stations at the bottom of each one are shown with their codes. And the treated roads are shown in yellow. The permanent roads that are going to remain in the watershed are in black. There's one going right up the middle of the watershed, and then a short piece in the upper headwaters that is going to be treated still, the red one right there. So I'm going to be showing some data about these gauging stations and the characteristics of the watersheds upstream. So here's a bunch of numbers, but one thing I want to point out is geology really caused some difficulties in trying to figure out what was going on in terms of the effects of road decommissioning. I use the terms road decommissioning and road removal sort of interchangeably. The Prairie Creek Formation, which is this column here, the percentage in each sub-watershed composed of that, has some aspects to it that are really prone to erosion. So you can see that the percentage varies a lot among the study areas. And the upper four of these are the tributary watersheds. And this is a sort of an unmonitored area of interfluves. And then the basin outlet is down here at what we call LMC, Lost Man Creek. And if any of you are familiar with that part of the Highway 101, it's right where the old Prairie Creek fish hatchery was. That's where Lost Man Creek joins Prairie Creek. So, and there were two control watersheds. It was kind of handy. We had watersheds that were draining effectively pristine areas. But you can see the vast difference in the amount of that Prairie Creek formation in these two. That kind of made them not very valuable in terms of control streams, at least in the context of the analyses I did. Somebody could probably take this data set and do more with it, but it didn't work out at the level I worked with the data. And this lower graph here is the progress of the road decommissioning program, starting in 2000, going through 2010. And this 81 kilometers total is about 95% of the road network in that watershed. So here's what an outslope section of road looks like. This is not a stream crossing, it's just a length of road between stream crossings. And the fill is pulled back from the outward edge and placed back at the uphill side of it. And in this case, Redwood National Park does a lot of mulching. Sometimes they put very heavy volumes of mulch to control surface erosion. Here's a stream crossing being excavated. There's more outslope road in the background, and there's a person here for scale. Right there. I think that might be Neil. Anyway, so the digging is going on still, or maybe this is post-digging and placement of large woody debris in the crossing itself. Some crossings had rather minimal amounts of wood put in them, and some areas left unmulched. Others had lots and lots of wood put in them, depending on what was available nearby. So part of the monitoring was on-site, and we actually had a contractor do this for us, where they would go out during storms and take manual samples of the water coming into a stream crossing excavation and the water going out. And of course they took the sample going out first, so they wouldn't muddy the water on their way up to the uphill side. And this is the data, not all the data, but the data that's sort of telling about this. Some of the increases in turbidity as water passed through a stream crossing excavation were quite large. And these are percentages, so you could say that, okay, it was 1 coming in and 100 going out, and well, that's a huge increase. But some of these numbers were quite large. Some of the turbidities coming out of the crossings were more than 5,000 turbidity units at times. But this study was, this part of the study was hampered in that we don't really know the hydrologic context of the points in time when these samples were taken. We know they were during storms, but because it's not continuous data, we can't really see the full extent of turbidity changes. But some were quite high, well over 1,000. And the trend here was that usually the first storm that was monitored, or the first storm of the season after restoration, had the highest response in terms of turbidity. And that waned through time. You can see that there's a very distinct trend among these guys right here, starting out very turbid and getting less so. In terms of stream crossing erosion volumes, there was a subset of about, I think, 22 where post-restoration and post-winter erosion volumes were measured, and it showed the same kind of skew that we see in all the other studies. One was a very bad actor at about 204 cubic meters of erosion. That's a lot of erosion from a stream crossing. And then they tapered it up quickly, and with several showing zero erosion. The downstream or off-site monitoring consisted of some turbidity recording stations, recording turbidity and discharge. And unfortunately, we didn't have pumping samplers like Liz talked about yesterday at Casper Creek. It was all manual sampling, but the contractor was quite dedicated, got out there and covered most of the largest storms pretty well. And so you match up the turbidity that's being recorded at any given moment, and this picture was taken right here on the recessional limb, well past the peak discharge and turbidity. You match those up with the lab data from the water samples on suspended sediment concentration, and you come up with a relationship that then you can use to turn those 10-minute turbidities that were recorded into 10-minute suspended sediment loads. Add them all up for a season, and that's the total load for that year. And each of the stations I showed on that map earlier with the station codes had this set up. So post-winter erosion, it varies depending on the strength of the winter and how many years have gone by since the work was done. Most of the erosion typically happens the first winter, even if that winter is not particularly large. But then the larger winters can come along and you can get a lot more. This particular crossing experienced some surface erosion and some rilling, and probably some channel erosion down here, but it gets a little hard to measure with that much wood. And this was not in Redwood National Park. This was taken elsewhere on somebody's post-restoration job, and basically it looks like, to me, an under-excavated stream crossing. In other words, they didn't pull all the fill out, and so it eroded. It's a lot more easy to measure when it's like this, but that's not the result we want. So over the course of the study, from when our study began in the fall of 2002, which is the beginning of water year 2003, water year running from October through the following September, we have the peak flows here, that's these darker gray columns in CMS, and the recurrence interval in terms of years, that's the inner white column here. So we started out with some relatively just moderate to small storms in the beginning, early years of this. And as I showed earlier, restoration ended in 2010. So these are post-restoration sort of follow-up monitoring years. And we just happened to have the largest flows of the whole study period during that part of it. And this lower graph here is the departure from the period mean for suspended sediment load and peak discharge. Okay, so I created a mean for all the, I think, 14 years of study, and this is the annual departure from that mean, either to the plus or the negative. So sediment load was really high compared to the peak flow in the first year of the study, and I'll get into that in the next slide. And then we had some dry years, and in 25 we had a very low peak flow but a high sediment load. And then as we go on, it starts to make more sense. They're either both on the plus side or both on the minus side of this departure. And as we progress through time, after the post-restoration period, we had some pretty high flows and less than the mean sediment loads. A low flow and a very low sediment load. And then the highest flow of the year really didn't produce much in the way of sediment. This is kind of the same data set, plotted with line graphs. First is the road length treated in terms of kilometers per square kilometer of the watershed. It varied a lot over the time. There were some years with little or no restoration. some high restoration years, and then the program ending right around here. Okay, thank you. I've also shown 10% turbidity here. That's just taking the whole winter's turbidity data set, 10-minute data, and computing that level of turbidity exceeded just 10% of the time. It gives you somewhat of a storm turbidity, but it's a way to summarize an entire year of turbidity data. I've used it before in some other studies. And peak discharge and sediment loads. Now this is suspended sediment. We did not measure bed load. Hardly anybody does that anymore. So in the early years, as I showed on the previous graph, we had some relatively high sediment loads for the discharge that happened. Well, two things were revealed after we saw the data come in and saw it was kind of strange. We went out and did some field investigations and found that there had been a debris torrent in preceding the winter of 2002, 2001, 2002. And that explained that high sediment load, and then there was a short recovery period, seemed to settle back down, and then there was a weir dam failure upstream of this lowest most gauge, Lost Man Creek, in 2005 that elevated sediment loads once again, both non-treatment related, nothing to do with watershed restoration. That one settled back down again, and then the only period really where I could sort of detect restoration effect might have been here in these several years, where road treatment was high and sediment loads went up correspondingly. But then again, so did peak discharge. So that's kind of a confusing thing there. And then later on in the study, we had less sediment load relative to peak flow. And that kind of trend continued all the way through virtually the present. So this plots road length treated or annual maximum peak discharge against suspended sediment load. So I was just trying to explore for relationships here, and there's no relationship between the suspended sediment load and the length of roads treated that I could discern, owing to those two weird events I mentioned back in the early part, and just a variable rate of road treatment, and who knows what else. There is a lot of legacy erosion happening in this watershed. We found some at various times. We didn't do a full watershed walk or survey to find all those sources, but we know they exist. But what did make a little sense was that if I separated the period and ran peak discharge against sediment load, there was a definite shift over time. In the earlier years, 04 through 09, thank you, there was a much deeper relationship indicating that for a given discharge there was a lot more suspended sediment transported and leaving the watershed than in the later period. As geomorphologists and hydrologists, we look for this kind of thing as a signal for what's going on in the landscape, and there was a very definite signal, I would have to say, in these data. Sorry. Okay, last slide. So the results, kind of what I already mentioned, on-site turbidities increased through the excavated stream crossings were initially really high and extreme in some cases, as that sort of recently treated soil was first exposed to high flows. A few stream crossings delivered a lot of sediment, most not that much. Downstream or off-site turbidity and sediment loads were proportional to annual peak discharge. Erosion from non-treatment features obscured treatment effects in the early part of the study period, and the response of annual loads to flood magnitude shifted through time, with loads declining relative to floods in the later years. Thank you.